So our next speaker is Masayuki Wasa from Boston College. So Masa has actually had a long tradition associated with C-H functionalization because he did his PhD with Jin-Kwan Yu at Scripps. And after completing his PhD, he then went to do a postdoc with Eric Jacobson at Harvard. And then obviously liked Boston and decided to stay in Boston and began as a professor at Boston College. And he's developed a very innovative approach to thinking about reactivity in general, and it also relates to C-H functionalization, where he's developing unusual paired cooperative catalysis involving sort of like frustrated Lewis acid type reactivity. So we're going to hear a really nice talk from him. Recent advances in enantioselective cooperative catalysis. Welcome, Masa.
Thank you so much, Professor Davis, for your very kind introduction. Can you hear me? Would you just verify with me they can hear?
Yes, we can hear you. You're fine.
That's good to hear. So it is truly my privilege to be able to share with you some of the recent advances we have made in the field of cooperative catalysis for late-stage C-H functionalization of bioactive amines. As you know, the tertiary and secondary and tertiary amines are ubiquitous in bioactive molecules of pharmaceuticals. Radioselective, yes.
Your slide is not shared yet. Your screen
is that right? Let's see. Do you see it?
Yes, now we can see it.
That's good to hear. Sorry about this problem. So secondary and tertiary amines are ubiquitous in bioactive molecules and pharmaceuticals. Radioselective and enantioselective functionalization of these sp3ch bonds that are contained in bioactive amines do represent a very compelling problem in the field, I find it fair to say. However, the development of catalysts that can do these desirable transformations have been very limited. That is first because obviously the secondary amines are Lewis basic. So if you were to take a Lewis acid catalyst, it can be readily quenched by the nitrogen center. As you see in the structures of these molecules typically possess both Lewis acidic and Lewis basic functional groups that can go about quenching the catalyst. However, today I would like to share with you our development of new class of cooperative catalysts that can achieve the radioselective, specifically alpha and beta selective, and sometimes enantioselective functionalization of these bioactive amines, tolerating all of the functional groups that they possess. The development of a catalyst that is capable of selectively activating these bonds have been hampered, as I said in a previous slide, by the fact the nitrogen center is quite strongly Lewis basic. Both of I will share with you two of our recently published work. Both of them are initiated by a Lewis acid, a very potent Lewis acid, abstracting a hydride from the tertiary amine substrate or secondary amine substrate to generate an ion pair constituting of iminium ion and a Lewis acid hydride. I would like to demonstrate to you in the presence of a chiral Lewis acid co-catalyst, we can achieve enantioselective alpha functionalization of amine. Alternatively, if you were to take a Bronsted basic co-catalyst, now you can functionalize the beta position of the amine. The identification of a Lewis acid catalyst that can abstract the hydride from the amine was a difficult part of this project. That is because a vast majority of the Lewis acid catalysts that may be potent enough to abstract the hydride from the amine can readily form a stable classic Lewis adder. Indeed, despite the recent advances made in the field of so-called cooperative catalysis, a vast majority of these catalysts contain very weakly Lewis acid or Lewis acid type catalyst units that do not get readily quenched by the basic, either basic catalyst, basic intermediate, or the basic product. As you see in the catalyst structure shown below, obviously these hydrogen bond donor catalysts serve as Lewis acid type catalysts, but these are obviously too weak to abstract the hydride from the amine to generate a cation. Many of the organometallic Lewis acid catalysts, such as the one developed by Shibasaki, also possess a soft Lewis acid catalyst, but these Lewis acid catalysts that is capable of working with the base are also too weak to abstract the hydride from the amine. As we were investigating which type of Lewis acid can overcome the undesirable mutual quenching, but instead go about promoting the hydride abstraction from the amine, we were inspired by this early work by Erker, in which he has synthesized this intramolecular frustrated Lewis pair constituting of organoborane and the tertiary amine that is proposed to undergo hydride abstraction in the intramolecular fashion to generate the deuterionic intermediate containing an iminium ion and the boron hydride. Although this intermediate could not be isolated nor characterized, in the presence of an unsaturated compound such as an aldehyde, they were able to obtain a deuterionic product containing the iminium ion. Despite this seminal discovery, the utilization of the iminium ion derived from the amine in this fashion has never been investigated in the context of enantioselective and catalytic alpha amino CH functionalization reactions. So that's where we actually saw the opportunity. Our very recently published report involves the reaction of an amine substrate, a broad array of amine substrates that can react with a trimethyl substituted alkyne in the presence of 3-pentaphenylborane and a chiral organocopper complex, also in the presence of an alcohol additive. What we propose happens here is that 3-pentaphenylborane abstract the hydride from the amine to generate the ion pair constituting of iminium ion and a borohydride. At the same time, we propose that the organocopper species can undergo transmethylation with the thioalkynyl complex in the presence of an alcohol so that you would generate a chiral nucleophilic alkylation agent. Now the stage is set to promote the enantiodetermining C-alkyne bond-forming reaction between the organocopper species and the iminium ion to afford the desired product. Through this approach, when we reacted the bioactive amines containing either tertiary or secondary amines, we have demonstrated that we can install the desirable alkyne unit while tolerating a broad array of Lewis acid and Lewis base sensitive functional groups. You may notice that in the presence of, let's say, the first molecule that possesses both benzylic and allylic as well as N-methyl CH bond, the N-methyl position is selectively undergoing alkylation. This could be because that the corresponding iminium ion generated through either the benzylic or allylic CH abstraction would be stabilized through the conjugation to the neighboring pi systems, while the N-methyl derived iminium ion is the most electrophilic. However, in the case of cinacalcid that does not possess the N-methyl group, then the alkylation does start to take place of the di-substituted carbon. So the installation of the utility of these newly installed alkyne, of course, I don't think you might be insulting to say what the utility of these alkyne units are, but you can also use those newly installed alkyne in the context of Crick reaction to install, let's say, biotin, PEG3. We have also been able to achieve this transformation in the enantioselective manner. Let's say if you were to take an amine substrate in the presence of a di-TMS substituted alkyne, in the presence of 3-pentaphenylborane and a copper chiral pi-box complex, you can achieve the enantioselective alkylation reaction to afford the desired product in as high as 95 to 5 ER. We actually have done a thorough mechanistic investigation for this chemistry. We wanted to know what the rate determining step is. So one of the first experiments we did was to determine the KIE. When we went about doing the independent rate measurements, we did not observe a KIE as the KH over KD was 1.02. However, what we noticed was that when we do the competition rate measurements, we observed the KIE of 4.4. This is consistent with a mechanistic scenario in which the turnover limiting step is prior to 3-pentaphenylborane catalyzed hydride abstraction, and also that 3-pentaphenylborane catalyzed hydride abstraction is reversible. To determine really what the determining step is, we have also determined the dependency of the concentration of these of the reactants or the catalyst to the reaction rate. What we have found was that the reaction shows zeroth order dependency on the concentration of amine, copper xanthos complex, as well as on the alcohol. However, we see a 0.5 order dependency on the concentration of 3-pentaphenylborane and first order dependency on the concentration of alkynyl silane. These observations seem to be in agreement with the hypothesis is that turnover limiting step is prior to 3-pentaphenylborane catalyzed hydride abstraction, which is consistent with the KIE results, and also that there may be a resting state complex that contains 2 molecules of 3-pentaphenylborane, which accounts for 0.5 order dependency on the concentration of 3-pentaphenylborane. Based on these kinetic data, we propose the following mechanism. The literature precedents show that when you were to react either alcohol and water with 3-pentaphenylborane, you would form this resting state molecule possessing 2 molecules of 3-pentaphenylborane. This can release the complex 1 containing the boron hydroxyl intermediate, which can then undergo the turnover limiting reaction between the TMS substituted alkyne and the boron hydroxyl species to generate a boryl alkynyl complex, which then we propose undergoes transmetallation between the organocopper intermediate. So now you will go about generating the chiral nucleophilic copper alkynyl intermediate, which then releases 3-pentaphenylborane also that can now abstract the hydride from the amine to generate the electrophilic iminium ion and the copper alkynyl complex, which then undergoes the desired CC bond forming reaction in the enantioselective manner to give the corresponding product. So far, I hope I have been able to convey to you that the cooperative function of a chiral organoborane and a chiral Lewis acid co-catalyst can be used for enantioselective alpha functionalization of amine. However, there are actually many catalysts. For instance, Professor David has reported some seminal examples of dirodium catalysts, chiral catalysts that can achieve enantioselective alpha functionalization of amine. But the beta position of amine is a true sp3 bond that is really difficult to access. What we thought about was that the in situ generated iminium ion through the Lewis acid catalyzed hydride abstraction now possesses a very acidic CH bond adjacent to the iminium ion. What we thought was that we may be able to take a bronze basic co-catalyst that might go about deprotonating the now acidic CH bond to convert the iminium ion into the enamine. Subsequently, in the presence of a suitable electrophilic entity, we may be able to let the enamine attack the electrophilic entity to forge the desired CC or C heteroatom bond. Based on this hypothesis, we recently developed a method where we go about taking a broad array of bioactive amines and reacting it with an in situ generated electrophilic D+ equivalent in the presence of 3-pentaphenylborane and the bronze basic catalyst. The question becomes, why would you like to incorporate deuterium at the beta position of the bioactive amines? One utility of the deuterated bioactive amine at the beta position is that those deuterated molecules can be used in the context of isotope labeled internal mass spectroscopy, or alternatively, if you could install a tritium at the beta position, you can also use the molecules for ligand binding assay. So these molecules may find applications in drug discovery. The way we went about achieving this transformation was through the reaction of amines in the presence of D-acetone. We react these substrates in the presence of 3-pentaphenylborane and a bronze-based catalyst so that in situ, we go about letting 3-pentaphenylborane activate the ketone, drastically lowering the pKa of the alpha CD bond so that the base can go about dedeutyrating it, so that you generate an ion pair constituting of D-ammonium ion and then the boron inorate. At the same time, 3-pentaphenylborane may abstract the hydride from the amine, and then the base might go about deprotonating the iminium intermediate so that you can convert various amines into the corresponding enamine. Now, the stage is set to react the nucleophilic enamine with D-ammonium ion. If this CD bond forming reaction happens, the subsequent protonation of the boron inorate would degenerate the catalyst while giving the protonated carbonyl compound and then releasing the active catalyst. Using this approach, we have learned that reacting the amine with about 7 equivalents of D-acetone in the presence of 10% of 3-pentaphenylborane as the only catalyst, we can go about incorporating deuterium at the beta position in very high efficiency. As you may see, this method can tolerate a broad array of functional groups such as cyano group, esters, amides, secondary amines, as well as ketones are well tolerated to give the corresponding deuterated product in high efficiency. You might also notice in the case with the last molecule the alpha position of the ketone and also undergo deuteration, which may not be entirely surprising considering that these catalysts, the amine substrate or amine product serve as a ground state base in this case, can go about dedeutyrating acetone. The reaction can tolerate secondary amines and various functional groups, but it is more efficient in case you go about protecting, let's say, alcohol in the form of TBS ether. The reaction also works with a broad array of cyclic amines also. Here, the wide variety of functional groups, as shown in the previous slide, can be tolerated. In the case with paroxetine, which possesses a more sterically hindered beta amino CH bond versus the more exposed one, selective dedeuteration of the secondary carbon was observed, while the epimerization of the other position, nor the deuteration of the C3 position was observed. So today, I hope through this short presentation, I have been able to convince you that the cooperative action of 3-pentaphenylborane and the titled Lewis acid co-catalyst, or the combination of 3-pentaphenylborane and the base, can go about converting amines, including many bioactive amines, into the corresponding iminium ions or enamines, while tolerating, while overcoming the undesirable mutual quenching with a broad array of functional groups and heterocycles. Now we are expanding the scope of both the nucleophilic and electrophilic entity so that we can go about installing even more desirable functional groups such as the fluorine, radioactive fluorine, or CF3 containing functional groups, and so on. I would like to conclude this presentation by quickly thanking my coworkers in my lab. Dr. Min Shang was a spectacular postdoc, as well as Dr. Chang and Yejing, Min Kao, and others. I sincerely appreciate, and I would like to acknowledge them for their productivity and also their commitment in science. I would like to thank my coworkers here in Boston College who have made 4 years of my tenure track appointment a very enjoyable one, especially my colleague, Professor Hobeda, who served as my junior investigator's mentor. I would also like to thank the funding agencies, NIH and Sloan Foundation for in the Boston College for providing the funding for the research project that I was able to discuss with you today. Finally, I would like to thank the organizers once again for your very kind invitation, and I will be more than happy to answer any question that you may have. Thank you so much.
Thanks for a great talk, Masa.
Thank you so much, Hugh. I appreciate it.
So it's really interesting how you can get the poly conversion deuteriation at different sites. Have you looked at modifying the type of Lewis acids and to change that distribution ratio, and what type of control is possible?
Thank you for that question. We have indeed, not necessarily in my group, but there actually has been many groups, especially in Europe, who have developed many derivatives of 3-pentaphenylborane. Very few of them are actually commercially available, but they have also been studied in the context of hydride abstraction chemistry from the amines also in a stoichiometric manner very many times. What we have learned through our studies is that, let's say we have gone about converting the para-fluoro group to a para-CF3 group. It happens that the functional group tolerance becomes much inferior when you were to generate a more strong, even stronger Lewis acid. 3-pentaphenylborane is very unique, as I told you, in a way that it is potent enough to abstract the hydride, but it can go about overcoming the undesirable mutual quenching with a broad array of Lewis acid sensitive functional groups. It's just when you go about making it too strong of a Lewis acid, the functional group tolerance will be lesser. And if you were to make it into a lesser Lewis acid, for instance, VPH3 does not even abstract the hydride from the amine. So we are playing in this narrow merging, it looks like, where the modification to the organoborane catalyst structure is actually not very well tolerated.
Okay, thank you. And there's a question here from Joshua Lane Martin, which I think will confirm what you just said now. He's asking, does the deuteriation reaction work using BF3 etherate?
It does not. We have tried BCl3, we have tried BF3, and then an array of other Lewis acidic organoboranes. We have also wondered whether we can do some of these reactions in an anti-selective manner, anti-selective deuteration. So we have tried the CVS catalyst derivatives, but none of them seem to promote the desired hydride abstraction.
Okay, And then we got a question from Yunjai Shim, who says, first of all, thank you for a great talk. And he was curious about how sensitive the reactions are to the quality of the boron perfluorophenyl group.
Trispentophenoborane. So indeed, it is somewhat sensitive to it. It likes to form, just like when I showed in the mechanistic study for the alkylation reaction, it does like to form a complex with water. And under thermal conditions, the water complex of trispentophenoborane is prone to undergo decomposition, undesirable decomposition, and it will not regenerate it back. So we make trispentophenoborane in-house, and we have also bought one from TCI. We actually have a good discount from them, so that's where we usually buy it from. But the one from TCI is of excellent quality. While I would not name which vendor, but some vendors, trispentophenoborane, we have evaluated them, and they are far inferior to the one we have made or the one we have purchased from TCI. So indeed, it is quite dependent, it's fair to say, on the quality of trispentophenoborane. How was it made? How much impurity does it contain? And how much of it may be the complex of water and trispentophenoborane?
Okay, great. Then another question from Nicholas Chiappini. Enjoyed the talk, Masa. With the deuteriation work towards the end of the talk, does the source of deuterium affect the performance? Does deuterated methanol work?
Thanks for that question too. D-methanol is known to form a complex just like water does with trispentophenoborane, while D-butanol has a much weaker affinity to do so. So T-butanol, or I should say OD, T-butanol does work quite effectively, but not D-methanol. We have also learned that we can actually use D2 as a source of deuterium. In that case, you actually get the both alpha and beta deuteration, but SLP systems, as shown by the group of Stefani and Alcar, can go about splitting D2 and T2 also. So you don't actually have to depend on D-acetone, although it's a cheap source of deuterium, D+, but we eventually want to apply this method for tritiation chemistry. In that case, the T-acetone is just not an accessible molecule, but T2 would be a good additive to have. So yes, it is very much dependent on the source of D or T. And then perhaps the cheapest one you can use would be the D2.
Okay. Then one final question from Tito Akindele. Is the reaction applicable to the synthesis of tertiary alpha substituted amines?
So fully substituted carbon center. I think that's what the question is. So as far as we know, this trispentophenoborane is not able to abstract the hydride from a tri-substituted carbon center. If it does, we would actually have issues in this enantioselective alkylation chemistry, where you do set the tertiary center, and if this CH bond adjacent to the nitrogen were to undergo hydride abstraction, most likely we are going to see an epimerization of the stereogenic center. So although there has been cases demonstrated by other groups, when you have the phenyl unit instead of the alkyne group, you may be able to abstract the hydride from there. But I've never seen an example where you go about generating a fully substituted alpha carbon center, especially in the enantioselective fashion. But I entirely agree that that would be a very appealing transformation. If you were to design less statically hindered organoborane that is potent enough to abstract the hydride, I think there is a possibility that you can also functionalize that position also.
Okay, great. Well, thank you for a wonderful talk. There's still some questions in the chat room, so please go and look at those as well.
I'll do.
So congratulations for a great talk. And if you're still on Menti, please join me in recognizing this great talk as well.